Yeah, hello everyone, welcome back. So let us start with the next topic. So today we are going to do birthday paradox. Birthday paradox. First, let us understand what is the meaning of this birthday paradox. It is one of a good examples to visualize the application of probability theory in the cryptography. Um, it is also useful to check the security of a crypto system under the collision attack called a birthday attack. Okay, so suppose consider a function. I'm having a function from x to y, where y is the set of n distinct element. Y has the cardinality of y is, I'm saying, n. Okay, so what is birthday paradox? It is how many distinct value we have to choose uniformly. How many distinct value we have to choose uniformly from x so that we get a collision of f, so that we get a collision of f with certain probability bound, with certain probability bound. Okay, that means I have to find what is the set I have to consider, what are the number of element I have to consider in x so that I get a collision. So if we consider x as a group of people, the image f of xi is birthday of the ith people. If you consider like that, say this x is group of people, and say f of xi is birthday of ith people. Okay. So and y is the set of n different birthdays. Then birthday paradox becomes what is the minimum number of people, and if you want to write, so the birthday paradox is what is the minimum number of people, sorry, necessary in a group, necessary in a group for the fact that probability that two people have same birthday, probability that two people have same birthday is greater than some fixed epsilon, is greater than some epsilon, is greater than epsilon will be decided already. Okay, so actually I'm not going to prove whole birthday paradox, but I just want to give you a glimpse expression which can be done. Suppose we choose k people, suppose we choose k values of xi. That means I would like to find the value of k and how this k is dependent with your n and epsilon. So with the birthday paradox, it has been said that k should be greater than equal to 1 plus root of 1 plus 8n log 1 upon 1 minus epsilon and the whole divided by 2. So this is what k value of k should be. It should be greater than this. Now if you take epsilon equal to 1 by 2, then this will be approximately equal to root n. Actually k will be approximately near to root n. That means, for example, if you take that means that if you take root n number of element from x, if you take root n number of elements from x, then there is more than 50% chance that we get a collision. We get a collision. That means if of two people have same birthday, xj, for some xi is not equal to xj. Yes. For example, if you take n equal to 365, then if you're taking epsilon equal to 1 by 2, then your k should be greater than equal to 23. If you apply the same formula, you should take your k as greater than 23, so that you'll get a 50% chance of getting a collision having same birthday. Okay, so the next thing is perfect secrecy. Perfect secrecy. Yeah, see, the perfect secrecy was proposed by Shannon. So consider a crypto system. Consider a crypto system PCKED, okay, where your P is the plaintext space, C is the ciphertext space, K is representing key space, and E and D are the encryption function and decryption functions. So since the plain text, key, ciphertext, we are having suppose English letter, correct? So I'll quickly directly go to the definition of perfect secrecy. A crypto system has perfect secrecy. Perfect secrecy if conditional probability of x given y is equal to probability of x for all x belongs to P and y belongs to C. So that is the meaning of this. That is posteriori probability that the plain text is x, given that the ciphertext y is observed is identical to identical to the priori probability that the plain text is X. That the plain text is X. That means given the cipher text, whatever information you are getting for the plain text, it should be same as the probability for the plain text. Yes. Okay. So there is one more one theorem we're having. A crypto system PCKED, where you say cardinality of key space is same as cardinality of ciphertext space, same as cardinality of probability, provides perfect secrecy if and only if every key is used with equal probability that is 1 upon mod k, and for every x in P and for every x in P and y in C, there is a unique key k. There is a unique key k belongs to the key space such that ek of x is y. Then only it will be a perfect secrecy. That means what? For every encryption I am using different keys, correct? There is no key which is used twice. So with this theorem, there is a crypto system which is based on this, that is called OneTime OneTime pad. OneTime OneTime pad. It was proposed by OneTime in 1917. Gilbert OneTime. Okay, so in this crypto system, your plain text space, your ciphertext space, and key space, everything is having the same 0 1 power n. That is maybe n bit length, if you say. So thus in OneTime pad, we encrypt a bit string of length n using a key of n bit, and the ciphertext is n bit. That means your plain text is n bit, your key is n bit, and your ciphertext, whatever you are getting, that is also n bit. Okay. So before encrypting X, the sender first chooses a share of secret key K, share of secret key K, that is uniformly. This belongs to means uniformly random. So once they have decided the key, how they are going to encrypt, encryption is easy. What they are going to do, they are going to just XOR XOR key. What do you mean by XOR? Suppose I'm having one XOR with 1, I will be getting 0. If I'm having one XOR with 0, I will be getting 1. If I'm getting 0 XOR with 0, I will be getting 0. So see, there is no carry forward. 1 XOR 1, it is getting 0. So this is what your XOR means. And this XOR is component wise. See, X is n bit, K is n bit, so it will be XORed component wise. In the case of decryption, what happens? You just having, after getting the cipher text, that is Y, so this value whatever it will be your cipher text Y, so you just put decryption of Y, you XOR it the key, the receiver will XOR with the key K, and they will get the decryption of Y. The plain text will be obtained. So it is very simple. See, for every encryption your key will be used one time. That's why it is called one time pad. So we can choose n bit from 0 1 raised to n in 2 raised to n different ways. Hence the shared secret key are uniformly distributed. Every key has the probability of 1 by 2 raised to n. So by Shannon theorem, this is the perfect, this satisfies the perfect secrecy. Okay. Varnam one time pad is perfectly secure. But there is some drawback. And see, when Varnam introduced his crypto system, he conjectured that the crypto system is perfectly secure and no one can break his crypto system. But he failed to prove this conjecture. After 40 years of Varnam one-time pad, in 1949, Shannon proved it. Shannon proved that Varnam one-time pad has the perfect secrecy. 1949. Shannon proved this statement. One of the drawbacks of this crypto system is that encryption key can be used only once. The main drawback is that encryption key can be used only once. That means once you have encrypted a message with a key, you cannot use the same key again. Correct? For every message, our key is again different. That's why it is called one-time pad. And due to this, the crypto system is impractical, because practical situation, I may not have a n bit message and I'll be requiring a n bit key. Suppose 1 GB size is the message, then I require 1 GB size of key space key. That is difficult, correct? So due to this, crypto system is impractical. Just one pair of plain text and ciphertext is sufficient to obtain the shared secret key. If you get any one pair of the plain text and ciphertext, you can get the key. Just you XOR with the message, you XOR with the ciphertext, you will get the key actually. Thus, the known plain text attack is possible in this case. KPA is possible. Okay, hence repetition of the key is not allowed here. Okay, next is one more topic will start, that is random number generator. Random number generation. See, in the construction of one-time pad and many other cryptographic application, that is key generation in AES, DES, etc., we need to generate a random number of given size. For this, we first generate a random bit string of size n. Let the random bit string is say b1, b2 up to bn. You generate a random bit string, say b1, b2 up to bn, and then compute a, which is your I equal to 1 to n, that is bi 2 raised to I minus 1. You'll get the number. This number is randomly generated. It's because of this bit, random bit string, I have to get random bit string. Okay, now the question is how to generate a random bit string. How to generate this bit string, because if I'm having this random bit string, I can get the number, get the integer. But how to generate this? So coin flipping is one of the good example where a random bit string is generated. So we flip a coin and see whether it is head or tail. For head we write 1, for tail we write 0. In this way, if we flip a coin n times, we can generate a random bit string of size n. But flipping a coin is not practical. In general, we need to generate bit string of large size using some secure software or hardware so that no one can predict the output of bits. It is time consuming to generate a true random number, so we use pseudo random generator. It is time consuming because I cannot keep doing this coin flipping to generate a n bit string. So if I'm having 256 bit, I have to flip the coin for 256 times, then I'll get a 256 bit. So it is time consuming. What I have to do, I have to give a software to do, but there is no software which can generate random numbers. So we are going to use a technique, and we use this as pseudo random number generator. We call it as pseudo random number. So in practical, there is no random number generator. What we have is pseudo random number generator. Yeah, generator. What is a pseudo random number generator? A pseudo-random number generator is an algorithm that produces a long sequence of bits from a given short sequence of random bits. Is an algorithm that produces a long sequence of bits from a given short sequence from a given short sequence of random bit called initial seed. It is called initial seed. The output sequence of the bit is not truly random but looks like a random sequence as it depends on the initial seed. See, initial seed was of short length but it was random. So the final one is also not completely random, but it is a look-alike random sequence. That's why it is called pseudo random number generator. So a non-secure example of pseudo-random number generator can be obtained as follows. Suppose we want to generate a pseudo-random number, say m. We choose any x naught. Yeah. We choose any x naught which is less than m as the initial seed and define this. Xn is equal to a xn minus 1 plus b modulo m. Okay, where a and b are given integers less than m, we run the algorithm for n equal to 1 to m. Run this algorithm, will get the values 1 2 3. I will get x1 x2 and up to xm. Okay, the output xn is a pseudo random number less than m. So every output x1 x2 x3, since our x0 was random, so everybody is random, and this is called actually pseudo random number which is less than m. It has been shown that any polynomial congruential generator in cryptography is insecure, hence the output bits are predictable with high probability. But this was a toy example to give you what is pseudo random number generator. So to generate cryptographic secure pseudo random number, either we use one wave function or an integrable problem in number theory. So this was the insecure. To make it secure, there are two ways. Either you use one wave function or based on some intractable problem. The well-known and popular pseudo-random generator is Blum-Blum-Shum. Blum-Blum-Shum. That is BBS. This is very popular pseudo-random number generator. Is based on pseudo random number generator, PRNG, quadratic residue problem. So in this technique, what happens? We first generate two large prime. We first generate two large primes P and Q such that P equal to Q equal to 3 modulo 4. This is called Blum integer actually. If your prime is satisfying this condition, then it is called Blum integer. Then we set n equal to PQ. Okay, the integer n of this type is called Blum integer. Is called Blum integer. Then we choose a random initial seed. Then we choose a random initial seed, say x0, which is randomly generated from Zn. Further, we define xi as xi minus 1 the whole square modulo n. okay, and bi as xi modulo 2. So whatever xi I will be getting from here, I'll be taking modulo 2, I'll get that xi. The pseudo random bits are this b1, b2, so on. This is the pseudo random bits. It has been proved that the BBS pseudo random number generator is unpredictable. You can never predict. So what is happening? I have initial seed x0. X1 will be x0 square. Then b1 will be x1 modulo 2. Then x2 will be x1 square, and b2 will be x2 modulo 2. So this is how we will be getting the pseudo random number generator. Okay, thank you so much.